this lesson, we are going to look at chemical equilibrium. Specifically, we are going to explain the concept of chemical equilibrium and write the expression for calculating the value of K, the equilibrium constant. When we talk about chemical equilibrium, there's a few things we need to note. The first thing is that chemical equilibrium is dynamic. This means that the reaction doesn't stop. So as fast as A is forming B, B is forming A. We'll explore the meaning of this in just a minute. When we are at chemical equilibrium, the thing that is equal are the rate of the forward and reverse reactions. So as fast as A is forming B, B is forming A. The other thing is that the ratio of the products to reactants is constant, and we'll actually learn how to set up an equilibrium expression to show this ratio between the amount of products to the amount of reactants. When we look at an equilibrium reaction, we notice that there's a different kind of arrow included here. This arrow, which has a right harpoon and a left harpoon, is known as an equilibrium arrow. And what this tells us is that the reaction is proceeding in both the forward and reverse directions. Let's explore this idea of dynamic equilibrium a little bit more. In our drawing, we have 10 people that are inside a room and 4 people that are outside the room. So that we can see how the change is happening, the people inside the room are a different color than the people outside the room. What we're going to do is see what happens as this equilibrium progresses. And the key thing we want to note here is as we go through these examples, the number of people in the room and the number of people outside the room are constant, but the specific people in the room and the specific people outside the room are different. So here we see 2 people have swapped places. One person who was outside the room has moved in and one that was in moved out. We still have a ratio of 10 in the room to 4 outside the room, but the specific people have changed. And this will continue. Now we have 2 people that were originally outside the room in the room and vice versa. Now we see that we've gone to 3 people who were originally outside the room to being back outside the room. Again, we're at 2 people who were originally outside are now inside. Now 3 people who were outside are inside. Now all 4 people who were outside are inside, but it's constantly changing. So we have a system that's at dynamic equilibrium. The same number of people are always in the room, the same number of people are always outside the room. And what we see is that the rate of the forward and reverse reactions are equal. In this case, our forward reaction is indicated by somebody leaving the room. Our reverse reaction is indicated by someone entering the room. And we see that as fast as one person leaves, another enters. So the number of people inside the room and outside the room are constant. They're not equal to one another. It's the rate that's equal, but there are different people in and out of the room at any point along the way. This will continue on to maintain a dynamic equilibrium. So what does this look like when we talk about a chemical reaction? So let's look at a reaction where we're dealing with N2O4, and it breaks down or decomposes into 2 NO2 molecules. When I look at a graph of the data, I see that I originally start with some N2O4. So we see there's 0.05 molar N2O4 present. And we're not starting with any NO2. We're starting at 0 NO2. Initially, I see that the amount of N2O4 is decreasing and the amount of NO2 is increasing. And this will continue until a system gets to equilibrium. At the beginning, we're not at chemical equilibrium because we're still seeing the amount of N2O4 and the amount of NO2 change. But when we get to that equilibrium point, we'll see that there's a ratio of products and reactants that becomes constant. So if we look at about the point indicated here on the graph, this is about when we see that the amount of N2O4 stays the same and the amount of NO2 stays the same. If we were to zoom in and able to tag individual molecules, we would see, for example, that sometimes a nitrogen atom is present in NO2, and sometimes that same nitrogen atom is present in N2O4, just like we saw different people inside and outside of the room. It's not that the reaction stops, it's that the rate of the forward reaction, so N2O4 becoming NO2, and the reverse reaction, NO2 becoming N2O4, are equal. So the forward and reverse reactions are happening at the exact same rate, but the reactions are still occurring. Let's look at how we set up an expression to tell us something about the equilibrium constant K, which gives us the ratio of products to reactants. And that's what we're going to be worried about, that ratio of concentrations. The first thing we want to do is look at our generic reaction here. So we have our reactants on the left side of the arrow. Okay, so our substances A and B indicate our reactants. On the right side, we have our products, and those are indicated by the capital C and D. We also have lowercase letters in front of each substance, and those indicate the coefficients. We'll talk later about how we balance chemical equations to get those coefficients. Right now we'll be starting with a balanced equation. And so those coefficients tell us something about the amount of reactants and the amount of products. So coefficients are whole numbers such as 1, 2, 3, and so on. If there's no number shown, then that means it's a 1. So much like when we looked at charges on ions, where if it just had a minus or a plus, we knew that really meant a -1 or a +1. So in our equilibrium expression, what we do is we look at the concentration of products over the concentration of reactants. We can expand this expression depending on how many species we have. If we have 4 substances on the right side of the reaction arrow, then we can have 4 terms in the numerator. If we only have 1 term on the reactant side, we'd only have 1 term in our K expression. So this generic reaction is meant to be expanded or contracted depending on how many species we actually have present. Let's look at how we would apply this and write an expression for a specific reaction. So here we're going to look at our products first. So we have NO2. So we show NO2 as the numerator, and the brackets just stand for concentration. These can also be written for pressure, but we're almost exclusively going to look at examples where it's dealing with concentration. The 2, which is the number before the NO2, becomes the power to the concentration. So we have NO2 squared. N2O4 goes in the denominator because it's the reactant, and we always have products over reactants. And notice that there's no number in front of N2O4, which means it's a 1. So we have a power of 1, which we don't show. So we just have the concentration of N2O4 on the bottom. So if we had a reaction that had more reactants or more products, we would just simply continue this process for all of the products in the numerator and for all of the reactants in the denominator. Now we can look at a specific value associated with a particular equilibrium expression. We've already written our equilibrium expression based on the given reaction, and we have a value here for this particular reaction of 4.6 times 10 to the minus 3, and this value is going to be constant at a given temperature. We will also see that this value is different for every individual reaction. Let's look at the value of K here. We have 4.6 times 10 to the minus 3. So this is a very small number, much less than 1. What this tells us is that the denominator is larger than the numerator. In this case, the amount of NO2 is very small, and the amount of N2O4 is very large, because this would lead to a value much less than 1. So we would say this reaction favors the reactants because we have more reactants than products. For a reaction where the K value is greater than 1, that tells us that the numerator is greater than the denominator, which means there are more products than there are reactants.